In BARC scientist interview, they will ask you to draw graphs of complex situations without writing equations, without deriving the final expression. But in our educational system, like GATE like examinations, we memorize formula and we barely can draw graphs without deriving the final expression. But in BARC, you have to use your engineering intuition. And I am here to bridge this gap so that you can crack the BARC interview. That is why I have brought a complete series for heat transfer, fluid mechanics and solid mechanics, where I will show you that how to draw graphs. I will teach you from the basic that how to draw graphs without writing much equations, only using the basic equations and your engineering intuition. I have brought this course only for heat transfer right now, which will cost you exactly 499. But for the first 20 students, there is a flat 30% off and you will get it within 299. So grab it now. And in this video, I have put a sample of the same lecture series for heat transfer. See the lecture series. If you like it, then only grab it. Otherwise, jane to. Okay. So without any delay, let me start with the sample. So case for it is what? Now I will talk about a cylinder. So this is a cylindrical thing, okay, and this is the top view. Actually, if I draw the front view, then it will be something like this, okay, this and maybe this, right? So what I have drawn is, this is the front view, okay. So this is actually the wall, this is your wall, these things, this is also your cylinder wall, right? If I draw the 3D view, it will be like this. Sorry, okay, so there was not the screen, so it will be something like this, okay. So this one and maybe, yeah, this one, okay. This is the case. Now for this, you have to draw the temperature profile, okay. Again, you don't have to memorize anything. Again, only one thing you have to memorize, that is your Q is equals to Ka dt dr here. And what is r? This r coordinate is starting from here, it is starting from here, okay. So this is your r coordinate, okay, in the radial direction. But now, unlike the previous case, here the area is constantly changing, because area is 2 pi r into L. Obviously there will be a minus sign, okay, into dt dr, okay. So now you see that my q is equals to some constant 2 pi lk into r into dt dr, sorry, into r into dt dr, right? So this will be my case, and from here you know that, sorry about that, extremely sorry. So from here you know that if I write dt dr for constant heat transfer, it will be q by 2 pi lk, which is a constant, into 1 by r, into 1 by r. That means as my r is increasing, my slope has to decrease, and from here directly, if you call this as c, then my dt dr is equals to c by r. From this we can write that my t is equals to c ln r plus c1. You get the logarithmic curve. But what I am trying to say is, even if you don't know that it is a logarithmic variation, you know that this one, that will be the case, that my dt dr is proportional to 1 by r. This we know, right? This we know. So if we know this, now let me draw the graph. That this is my, so if this is my r equal to r1, this is my r equal to r2, okay. So maybe I have some temperature here, okay, some, if I draw it here, so here I have some temperature T1, and here I know that I have some temperature T2, right? So now you know that my slope will decrease. So let me draw three graphs. You will tell me that what will be the answer. One is this, another is this, another is this. Which one will be the answer? Let us see. You see that the slope here is constant. Slope here firstly is this, then it is this, then it is this, then it is this. So it is from this, it is becoming this. So the slope is increasing. What is the slope? This angle is the slope, and this angle, you see, this angle is increasing. But for this graph, this is the slope and the final slope is this. So this is the slope and the final slope is this. So the slope is decreasing only for this graph. So it will be a concave upward graph, right? If it is a concave upward graph, this is the answer. But now there is a catch. You see that this is a case when I have started it from r equal to r1 but not from r equal to 0. Why? So let us see that also. That for a very hot cylinder, initially a hot cylinder, okay? Initially a hot cylinder. Initially the cylinder was at 80 degrees Celsius, but the moment I say initially, that means it is a transient problem, unsteady problem. That means the temperature profile will change with time. So I tell you that you draw at t equal to 0.5 second what will be the temperature profile. So at t equal to 0, the cylinder was at 80 degrees Celsius, it is a solid cylinder, and you have to draw it at t equal to 0.5, maybe the ambient is at 25 degrees Celsius. Okay. So now we will draw it. So this is your r equal to 0, this is your r equal to maybe capital R, but now can you draw it like this? Can you draw it like this? The moment you draw it like this, they will ask you that, okay, what is the value of heat flux at r equal to 0? If you go to the previous formula, okay, that my temperature profile, if I follow this formula, then you see my dTdr shoots up to infinity. My dTdr shoots up to infinity, right? So that is what I am saying. If at r equal to 0 I have to have a finite heat flux, my dTdr has to shoot up to infinity, and that will be a very unphysical situation. Okay, because if my dTdr is shooting up to infinity, then mathematically you cannot define this q. You can say that my q will be finite because r equal to 0 and dTdr is infinity, but you cannot find the q, right? On the other hand, if my dTdr is constant, okay, then at r equal to 0, this is becoming 0, okay? But that is also not a physical case because you cannot say by any means that your dTdr is constant, right? So at r equal to 0, this situation cannot arise, okay? Another thing is that if you have a structure like this, so what do you expect? That will the temperature profile be something like this? From here it is here and then it is here. So then what is the heat flux? Can you define it? Because if you consider this graph, this is the slope. If you consider this graph, this is the slope. So at a particular point, two slopes are existing. Two slopes means two heat transfer. Is it possible? No. At a particular point, there will exist only one heat transfer value, and for that we know that is only possible in this case if the heat transfer is 0. If the heat transfer is 0, that means at r equals to 0, the slope will be 0. The slope will be 0, and you also know that from 0 slope it has to, the temperature value has to decrease. So the only possibility is this one, okay, where the slope is 0 here and it is decreasing. So for a solid cylinder, this has to be the graph, and this is a parabolic variation. So now if I tell you that by any chance you are drawing something like this, that you have a tank here, right, solid tank, and this has a wall thickness also, okay. So this is actually your tank. So it has water in it, and this is your wall, right? So again at time t equal to 0, my temperature was 80 degrees Celsius, okay, and my ambient is maybe 25 degrees Celsius, okay. Then you have to draw the graph only inside the cylinder. I am not going to the outside the cylinder where natural convection will take place, that I will take, okay. So here how will you draw? So if I now draw the graph, you see this is the axis, right, and this is my r, correct. So if I now draw the other important line, so this is maybe my r equal to r1, and this is my r equal to r2, okay, this is my r equal to 0, okay. So if I draw it, so I think you have understood the situation. Let me draw the graph very clearly, okay. So this is my TR plane, right, and this is r equal to 0, this is r equal to r1, this is r equals to r2, right. So now let me draw it once, just let me draw these vertical lines here. So here what happens? Firstly, again we know that this has to be like this, okay, and after that it is a logarithmic curve, so it will be something like this, okay. Okay, now this is the actual variation, and we know that this is my solid part, this is my hollow part, okay, or maybe this is my liquid, this is where the water resides, and this is the wall, of the cylinder tank, okay. This will be the variation, okay. So now again you have to understand that at this point, maybe if they ask you at this point, so are the slopes here and here same? They are the same. So let us see again, we have the Fourier equation. So for solid conduction or for any conduction in BARC, you have to only go to the Fourier equation, nothing else is required. So this is equals to what? Q by 2 pi Lk, right, into your 1 by r, right. I think this was the thing, okay, this was the thing, yeah, 1 by r. Now you see here r is equal to r1, at this point r is equal to r1, right. So if r is equal to r1, this value is fixed at r1, right. So then what is varying at this point? You see, in this region I have water, and in this region I have any solid material, so the k will vary here, right. So this k will vary here. So now my dTdr, my dTdr is varying with 1 by k, other than everything is constant, right. So it will vary like that. So here obviously if I consider that water has less thermal conductivity and this has more thermal conductivity, then this slope will have higher slope, so this water will have higher slope and this will have a lower slope, okay. This has to be there, and this is also true for a solid profile, okay. So from this exercise, if I tell you that if I have a solid bar, okay, like this, where the area is now varying, so let me draw it very clearly, okay. So this one, okay. So I have a solid bar, but now my area is decreasing, right. So area is a function of x, and again your T0 is mentioned, maybe your TL is not mentioned. Then you have to draw the graph. Okay,